This educational video has been brought to you by Chromperfect, the leading independent chromatography data system. In this video we will be using Chromperfect to demonstrate the topics being discussed. We will also review some academic images which are fairly low resolution. These are not indicative of Chromperfect output. However, they are useful to demonstrate some of the points of discussion. If you would like more information about our software, please visit our website at www.chromatographic.com or call 97358685551. This video is part 3 of a 3-part series and examines the entire principle of chromatography integration theory. It is recommended that you view parts 1 and 2, links in the description. Chromatography theory, Chapter 4 Integration theory, Part 3 Peak identification and quantification. This chapter explains the last 2 stages of the integration algorithm, peak identification and peak quantification. These stages require a calibration file but are unaffected by timed events. The calibration file contains a list of components. Each component has an expected retention time and a search window width. These are used in peak identification. Each component has a calibration curve, which is used in peak quantification. The calibration file also contains several properties that apply to all peaks, not just those identified as components: the area reject threshold, the standard injection volume, and the standard sample weight. It also contains the default component specification, which applies only to unidentified peaks. The theory of calibration curves and updates is covered elsewhere. In this chapter, it is assumed that the calibration file has been properly updated. The area reject threshold. The peak detection threshold in the method file is the primary defense against noise peaks, but this may fail when the signal-to-noise ratio is poor. The area reject threshold in the calibration file is the next line of defense. Peaks that have areas less than the area reject threshold are retained in the peak list but will not be included in further calculations. These peaks do not appear in peak tables, even if these list all peaks. Are not labeled in plots, although they have baselines. Do not contribute to the total area or height. Are not identified as components. The following figure shows a chromatogram with a noisy baseline and 3 small peaks. The area reject threshold has been deliberately set to a high value, so that the middle peak has failed to pass. The many fluctuations that do not have baselines all failed to pass the peak detection threshold. These are not peaks. The 3 fluctuations that do have baselines did pass the peak detection threshold. These are the 3 peaks in the peak list. The first and third peaks passed the area reject threshold, so they are labeled with the peak number. The middle peak has a peak number, namely 2, but it is not labeled because it failed to pass the area reject threshold. If the area reject threshold was sufficiently reduced, then this peak would be labeled also. If there is no calibration file, then the area reject threshold is 0, and all peaks with positive area will pass. Peaks, even negative peaks, normally do not have negative area. However, such abnormal peaks may be produced by poorly drawn manual baselines. In most cases, it is proper to reject these peaks, and a positive, or 0, area reject threshold is appropriate. If it becomes necessary to list peaks with negative area, then the area reject threshold must be set to a sufficiently large negative number. Retention time referencing. Peaks do not elute at the same time from one run to the next. The proper value of the search window width is determined by the amount of variation, jitter, in retention time that may be expected. When this variation is much less than the separation between peaks, then the search windows may be set wide enough to catch all variations and retention time referencing is unnecessary. When peaks are close together, search windows are not practical because they would overlap. Retention time referencing provides a way to adjust the position, expected retention time, of search windows so that they will track the variations in retention time. This allows the window widths to be reduced so that the windows do not overlap. Typically, one component is declared the retention time reference component. This component should elute in the same general part of the chromatogram as the components that will use it as a reference, ideally in a region free of other peaks. If other peaks are present, they must be significantly less than the candidate reference peak. Before assigning peaks to components, the integration algorithm first scans the component list for retention time references. If any components use another component as a reference, then the peaks under the reference components window are compared, and the peak with the largest area, not necessarily the centermost peak, is selected. If this peak's area fails to exceed the value of the reference peak area reject threshold, then no windows are moved. Otherwise, the ratio of the reference peak's actual and expected retention times is formed, and the windows that use this peak as a reference are moved proportionally. The three figures illustrate retention time referencing. The figure on the left shows an ideal chromatogram. Each peak is directly under its window. The figure on the right shows a similar chromatogram, but here the peaks eluted 10% early. Peak B remains under its window, but peaks A and C do not, so they are not identified. The figure below shows the same chromatogram with retention time referencing to component B. Here the windows for components A and C have moved along with the peaks, and all peaks are correctly identified. The retention time scheme works only when the source of the variation in retention times affects all the peaks equally, that is, in proportion to their retention times. Variations in the flow rate of the carrier gas or solvent fall under this category, but variations in oven temperature do not. In difficult situations, it may be necessary to use several components as retention time references, one for early peaks, one for middle peaks, and one for late peaks. The challenge is to find suitable reference peaks in a crowded chromatogram. The retention time scheme fails when the reference peak is absent, or the wrong peak is used as the reference. To prevent windows from being moved improperly, the reference peak area reject threshold should be set to a value large enough to prevent noise peaks from being considered reference peaks, but not so large that the real peak fails to be considered. In this way, if the reference peak is absent, the windows will remain in their original positions. Peak identification. The following section has already been published as a separate training video titled Chromatography Software, Peak Identification for GC and HPLC Analysis. Please use the timestamps below to jump to the next section if you have already watched this other video. The process of peak identification is straightforward. The governing calibration file contains a list of components, each of which has a specified expected retention time and a specified window width. Together, these determine the position and size of the search window for that component. It should be recalled that the expected retention time of a search window may be adjusted. See the section on retention time referencing. The process of peak identification starts with a chromatogram that has already undergone the processes of peak detection and peak integration. Each component's search window is examined in turn. If one or more peaks lie within the search window, then the peak that is closest to the center of the window, not necessarily the largest peak, is identified as the component. Identification is a one-to-one relationship. No component may be identified with more than one peak, and no peak may be identified with more than one component. This essentially simple process becomes complicated when search windows overlap. A peak that is under two windows may be the centermost peak of both. These conflicts must be resolved. By convention, the peak is assigned to the narrowest window, or the earlier window, if there is a tie. Each component gets only one chance to find a peak. If a peak is tentatively assigned to more than one component, then the component that loses that peak will have no peak at all assigned to it, even if there was another peak under that window. The following figure illustrates this problem. The search windows are located at 0.75 and 0.9 minutes. The peak at 0.81 minutes is the centermost peak for both windows, but it was assigned to the first window because that is the smaller, narrower, of the two. The peak at 1.00 minutes is not identified, even though it is under the second window. If the first peak were to elute earlier, say at 0.79 minutes, then it would still be identified as P3, but the second peak would be identified as P4 because it is centermost. The result is erratic peak identification, which depends on slight differences in retention time, and on the presence of other peaks. For this reason, overlapping search windows are discouraged. The calibration editor does not warn about overlap, but a cursory check will reveal most problems. If retention time referencing is used, overlap may happen because of the adjustments. Multi-peak search windows. By definition, no component may be identified with more than one peak. However, it is frequently of interest to consider all the peaks under a search window, and not only the centermost of these, the identified peak. In addition to calculating amounts for each identified peak in the chromatogram, the integration algorithm also calculates, for each component, the sum of the responses, either areas or heights, of all peaks that lie within the search window. This sum is the window response for the component. Next, using the component's calibration curve, the integration algorithm calculates the window amount for the component. These values are not reported in standard reports but may appear in formatted reports. Furthermore, if, in the calibration file, the quantization type of a component is set to multi-peak area or height, then two things happen. First, calibration updates use all the peaks that lie under the window to determine the response for that component. Second, peak tables in formatted reports can list single peak and multi-peak amounts and responses in a single column. Nested search windows. This feature was suggested by several customers in the petroleum industry, who wish to quantify a single peak that lies among several other peaks, which are to be quantified together. A typical example is the problem of the hexanes, or C6+ fraction. Several hexane and higher alkane isomers elute in a group. These are normally not resolved into individual components, but are converted to an area sum, then an amount is calculated with a common response factor. If this was the end of the story, then this calculation could be performed with a multi-peak window. But the same region also contains peaks due to aromatic components. These must not contribute to the C6+ fraction, instead they must be reported individually, using their own response factors. Although it has always been technically possible to perform such calculations in formatted reports, it has not always been easy to do so. The necessary formulas require knowledge of component numbers, so the format files work only with specific calibration files. Furthermore, not all situations have solutions. If the small window is adversely located relative to the large window, then peak identification does not always work as expected. These problems have been addressed in a coherent fashion. Two changes have been made in the peak identification algorithm regarding overlapping search windows. The first change affects peak identification. When search windows overlap, and a peak lies under both windows, the peak will be identified not with the closest component, as before, but with the component whose window width is least. The second change affects the window response. When search windows overlap, and a peak lies under both windows, the peak will not contribute to both components' window responses, as before, but to the window response of only one component. This may be the narrower, or the wider window, depending on the settings in the calibration file, as we shall see. When assigning peaks to search windows, the components are arranged in order of their search window widths, narrowest first. Each component gets to mark the peaks that lie within its search window. A component with a multi-peak window marks all the peaks that lie within its search window. A component with a normal single-peak window marks only its identified peak. Any other peaks within the search window are left marked as they are. Components respect previous marks. Since the smaller windows get to go first, their marks will not be overridden by later, wider windows. Therefore, peaks wind up under the narrowest window that may legitimately claim them. An example. The calibration file that was used in this example has 4 components. As seen in the column on the right, quantization is by area, 2 components have ordinary single-peak windows, and 2 have multi-peak windows. The third component, C6+, has a window wide enough to cover the windows of the other three components. The following illustration shows this calibration file applied to a chromatogram. We wish to report an amount for all the peaks under the C6+ window, blue, based on the sum of the peak areas, and using a response factor suitable for alkanes. We also wish to exclude several peaks from this multi-peak window, benzene, red, toluene, yellow, and the three xylenes, green. Peak identification does not involve peak selections. The colors are added for clarity. Furthermore, we wish to report amounts for these aromatic components, using individual response factors. The three xylenes will be reported as a single component. Here, in a nutshell, is how the peaks get sorted out. The benzene and toluene windows are the smallest, so they go first. These are normal single-peak windows, so they mark their identified peak only. The xylenes window goes next. It is a multi-peak window, so it marks all the peaks within its search window, the three peaks between 7.76 and 9.15 minutes. The C6+ window is largest, so it goes last. It too is a multi-peak window, so it examines all the peaks within its search window, every peak between 1.64 and 12.40 minutes. It marks all peaks that are not already marked by earlier, smaller windows. Therefore, in the end, the three narrow windows have their peaks, and the wider window has caught all the peaks not already accounted for. The standard report has a peak table that lists all peaks, much like the following. This table is not appropriate for multi-peak reports because it gives no indication of multi-peak relationships. A more suitable report will have a peak table listing all components and reporting both the area and the window area. For the first two components, benzene and toluene, the area and the window area are identical to one another and to the peak areas shown in the previous table. This is expected behavior for all nested single-peak search windows, where only one peak is involved. For the last two components, C6+ and xylenes, the area is less than the window area. This is expected behavior for non-nested single-peak search windows, and for any multi-peak search window, when more than one peak is involved. The area column shows the area of the centermost peaks. The values are identical to the peak areas shown in the previous table. The window area column shows the sum of the areas of all peaks that are legitimately under the window. In the case of xylenes, this includes peaks 17 to 19. In the case of C6+, this includes peaks 6 to 25, except for peak 7, benzene, peak 12, toluene, and peak 17 to 19, xylenes. Peak quantification. When a sample is injected into a chromatograph, the components within the sample are separated on the column and emerge at different times. A detector senses the emerging material and generates a response, usually a voltage. The plot of detector output versus time is called the chromatogram. If the components are well resolved, then each peak in the chromatogram represents one component, and the size of the peak is related to the amount of the corresponding component in the sample. Peaks may be quantified by area or by height. Issues discussed in this chapter are applicable to both area and height measurements. The term detector response, or simply response, may refer to either area or height. Quantification by area usually gives more reproducible results when peaks are well resolved and the detector is mass sensitive, for example with an FID or TCD detector. Quantification by height gives more reproducible results when peaks are poorly resolved, when the signal-to-noise ratio is poor, and when the detector is concentration sensitive and the flow rate is subject to variations. For example with a UV absorbance detector. Area is always given in units of microvolts seconds and height is always given in units of microvolts. Amount units are arbitrary, and can be either a mass unit, example milligrams, micrograms, micromoles, or a concentration unit, example micrograms per milliliter, ppm, if they are consistent. Peak quantification proceeds in two steps, the second of which is optional. First, the response is converted to a raw amount using the calibration curve. Next, the raw amount may be corrected for dilution of the sample and for variations in injection volume and sample weight. All these sources of variation directly affect the amount of analyte that is applied to the column, so it is appropriate to perform the corrections after the conversion from response to amount. This is particularly important when the detector response is not directly proportional to amount, as is frequently the case. The process of converting responses to amounts is best illustrated with an example. Consider a hypothetical component, using quantification by area, no internal standard, and a linear calibration curve through the origin and a single data point. If the data point has an amount of 100 micrograms and a response of 100,000 microvolt seconds, then the formula for this curve will be y equals 1000x, where x is the amount and y is the response. The calibration curve is shown in the following figure. Assume that we wish to quantify a peak with an area of 45,600 microvolt seconds. To find the amount graphically, find the point on the y-axis corresponding to the peak area. It is about halfway to the top. Move horizontally across the graph to the calibration curve, then drop down to the x-axis and read off the raw amount, which in this case is 45.6 micrograms. Of course, in this example the calibration curve is perfectly linear, and we could simply divide the response by the slope to get the amount. However, when the calibration curve is not linear through the origin, the math is not so simple. The conversion process is similar when the component has an internal standard, but in this case the calibration curve represents ratios. Again, the process is best illustrated with an example. Suppose that the hypothetical component described above is reference to a component that has a single data point with an amount of 1 and a response of 40,000 microvolt seconds. Therefore, the amount ratio for this hypothetical component is 100 divided by 1, which equals 100. The response ratio is 100,000 divided by 40,000, which equals 2.5. The calibration curve will be drawn through the origin, and through the point x, which equals 100, and y, which equals 2.5. The formula for this curve will be y equals 0.025x, where x is the amount ratio and y is the response ratio. Again, assume that we wish to quantify a peak with an area of 45,600 microvolt seconds, and further assume that the sample was spiked with the internal standard in an amount of 0.75, producing a peak with an area of 35,700 microvolt seconds. First, calculate the response ratio. 45,600 divided by 36,500 is equal to 1.25. Next, find the point on the y-axis corresponding to this response ratio. It is about halfway to the top. Move horizontally across the graph to the calibration curve, then drop down to the x-axis and read off the amount ratio, which in this case is 50.0. Finally, multiply the amount ratio by the amount of internal standard component in the sample. 50.0 multiplied by 0.75 is equal to 37.5 micrograms. This is the raw amount. The raw amount calculated above may be corrected for dilution of the sample and for variations in injection volume and sample weight. The corrected amount is then assigned to the peak. This is the number that appears in all reports. Correcting for dilution of the sample. Sometimes a sample contains more than the usual amount of analyte, enough to overload the column or detector. Such samples must be diluted until they produce peaks of reasonable size. The raw amounts are correspondingly reduced, but multiplication by the dilution factor generates the correct values for the final amount. The dilution factor acts as a multiplier in amount calculations. Corrected amount equals raw amount multiplied by dilution factor. For example, assume that the calibration standard with amount equals 100 is injected as a sample, full strength, and diluted 1:2, 1:5, and 1:10. 4 raw files are acquired and analyzed with their dilution factors properly set. The results are tabulated on screen. Note that the raw amount decreases with increasing dilution, but the corrected amounts are essentially identical. When using internal standards, the value of the dilution factor should reflect dilutions made before the sample is spiked with the internal standard. Dilutions made afterward affect analyte and internal standard equally, and do not affect the response ratio. These dilutions should not be considered when calculating the value of the dilution factor. Correcting for variations in injection volume. Up to now, it has been assumed that the injection volume was held constant throughout calibration and analysis. This is often not the case in actual laboratory practice, especially when the chromatograph is not equipped with an auto-sampler. Since most methods measure the analyte concentration, rather than its absolute amount, the injection volume is central to quantification and any inadvertent or deliberate variation in this volume must be considered. Small, inadvertent variations in injection volume occur whenever injections are performed manually since it is difficult to fill a syringe to an exact volume. Experiments have shown that reading a scale is more accurate than trying to fill a syringe. This means that precision is improved when the analyst does not attempt to obtain an exact volume, but instead fills the syringe to an approximate value, reads the scale to determine the volume, and uses the actual volume in subsequent calculations. When a sample is found to contain extremely high or extremely low levels of analyte, the analyst may deliberately alter the injection volume to bring the amount of analyte on the column within the useful range of the calibration curve. To correct for variations in injection volume, the integration algorithm must know both the standard and the actual injection volumes. The former is stored in the calibration file, and the latter is stored in the raw file. Therefore, the raw file and the calibration file must both support injection volume corrections before they can be applied. The correction factor is the ratio of the standard injection volume to the actual injection volume. If either of these numbers is 0, then no correction is performed. The standard injection volume acts as a multiplier and the actual injection volume acts as a divisor in amount calculations. Corrected amount equals raw amount multiplied by standard injection volume divided by actual injection volume. For example, assume that the same sample is injected 5 times, using 1, 2, 5, 10, and 20 microliters. 5 raw files are acquired and analyzed with their injection volumes properly set. The standard injection volume is 5 microliters. The results are tabulated on screen now. Note that the raw amount increases with increasing injection volume, but the corrected amounts are essentially identical. When using internal standards, variations in injection volume affect analyte and internal standard equally, and do not affect the response ratio. Therefore, this correction is not applied to internal standard amount calculations. Correcting for variations in sample weight. Sometimes it is desirable to report the results of an analysis in terms of the amount present per gram of original sample. To correct for variations in sample weight, the integration algorithm must know both the standard and the actual sample weights. The former is stored in the calibration file, and the latter is stored in the raw file. Therefore, the raw file and the calibration file must both support sample weight corrections before they can be applied. The correction factor is the ratio of the standard sample weight to the actual sample weight. If either of these numbers is 0, then no correction is performed. The standard sample weight acts as a multiplier and the actual sample weight acts as a divisor in amount calculations. Corrected amount equals raw amount multiplied by standard sample weight divided by actual sample weight. For example, assume that 4 samples of the same well-mixed powder are taken, worked up, and injected. The actual sample weights are 1.35, 1.53, 1.71, and 1.82 grams. 5 raw files are acquired and analyzed with their sample weights properly set. The standard sample weight is 1.50 grams. The results are tabulated on screen. Note that the raw amount increases with increasing sample weight, but the corrected amounts are essentially identical. The corrected amount values refer to the amount of analyte in the standard sample weight, in this case, micrograms per 1.5 grams of sample. Sample weight corrections apply equally to internal and external standard amount calculations. Sample weight corrections are often confusing to users, particularly when they attempt to calculate the proper value for the standard sample weight. Here are 3 examples that illustrate the selection process. Example 1. Calibration amounts are in units of milligrams. Sample weights are in units of grams. Amounts are desired in units of milligrams of analyte per gram of sample. No unit corrections are necessary, so the correct value of the standard sample weight is 1.0. For example, if a sample weighs 2 grams and has 10 milligrams of analyte, then 10 milligrams multiplied by 1 divided by 2 grams equals 5 milligrams per gram of sample. Example 2. Amounts are desired in units of milligrams of analyte per 100 grams of sample, frequently referred to as milligram percent. The correct value of the standard sample weight is 100. For example, if a sample weighs 2 grams and has 10 milligrams of analyte, then 10 milligrams multiplied by 100 divided by 2 grams equals 500 milligrams per 100 grams of sample, which is equal to 500 milligrams percent. Example 3. As above, except sample weights are in units of milligrams and amounts are desired in units of milligrams of analyte per kilogram of sample. The correct value of the standard sample weight is 1 million, the number of milligrams in a kilogram. For example, if a sample weighs 2 grams and has 10 milligrams of analyte, then 10 milligrams multiplied by 1 million milligrams per kilogram divided by 2,000 milligrams equals 5,000 milligrams per kilogram of sample. The combined correction equation. When several corrections are applied to the same peak, each acts independently of the others. The formula for the combined corrections is as follows. Corrected amount equals raw amount multiplied by dilution factor multiplied by standard injection volume divided by actual injection volume multiplied by standard sample weight divided by actual sample weight. The default component. Most chromatograms contain at least a few peaks that do not lie under any search window. Normally, these peaks are not quantified and have amounts of 0. However, it is possible to force unidentified peaks to be quantified using one component's calibration curve. That component is the default component. The calibration file determines the choice of default component. It may designate any single component as the default component, or none. Alternatively, it may specify that each peak should use the previous, the next, or the nearest component. If the previous component is specified, then peaks that elute before the first search window will nevertheless use the first component as their default. Similarly, if the next component is specified, then peaks that elute after the last search window will nevertheless use the last component as their default. In formatted reports, unidentified peaks also reference the default component's internal standard, group number, low and high alarm limits, and component constant. Note, if the default component is the nearest component, and an unidentified peak normally elutes halfway between two components, then the choice of the default component is uncertain. From one run to another, the unidentified peak may be quantified with either the previous or the next component, according to small variations in retention time. Window amount and window response. In addition to calculating amounts for each peak in the chromatogram, the integration algorithm also calculates, for each component, the sum of the responses, either areas or heights, of all peaks that are within the search window. This sum is the window response for the component. Next, using the component's calibration curve, the integration algorithm calculates the window amount for the component. These values are not reported in standard reports but may appear in formatted reports. If two windows overlap, and a peak lies under both windows, then that peak will contribute to both components' window response and window amount. Therefore, the total of the window responses may be more than the total response of all peaks. Normalized quantification. Some applications require that the results be reported in terms of a percent of the whole. This is called normalized quantification. Chromperfect supports three types of normalized calculations: area, height, and amount percent. All three normalized values appear in the footer of the standard report. Quantification with area percent or height percent requires no calibration file. Area percent is most appropriate when the detector response is essentially identical for each component. Area percent is calculated as follows. Area percent equals 100 multiplied by area of this peak, divided by total area of all peaks. Height percent is essentially similar to area percent. It is calculated as follows. Height percent equals 100 multiplied by height of this peak, divided by total height of all peaks. Amount percent is most appropriate when the detector response is not uniform for all components. It is calculated as follows. Amount percent equals 100 multiplied by amount of this peak, divided by total amount of all peaks. Of course, for amount percent to be meaningful, all the amounts must be expressed in the same units. In the calculation of total area, total height, and total amount, internal standard peaks and peaks with areas below the area threshold are not counted.